Okay, so talking about ionic compounds dissolved in water. Ionic compounds dissolved in water. We've seen this video before, lots of times maybe, where you have a salt, which is in a three-dimensional lattice, and we place it into water, and water molecules surround the ions in such a way that the partial negative charges are surrounding the positively charged sodium. Partial negative charges are partial negative charges here surrounding the positive. Partial positive charges here surrounding the negative chloride ion. Okay? So we have this understanding of how water molecules tear apart sodium chloride crystals or soluble ionic compounds, right? The same thing happens with sugar molecules. Sugar molecules don't reside necessarily in three-dimensional lattices. They can. You can find a crystal of sugars, but usually sugars is a solid. And when we talk about three-dimensional lattices, like we talked about our unit cell before, it's not going to be three-dimensional lattices of individual atoms. It's going to be three-dimensional lattices of molecules of sugar, right? But those molecules of sugar can be dissolved in water in the same way. Here we have it simplified, right? The negatively charged oxygens are around the polar side, or the positively charged side of this molecule, and the positively charged portions of oxygen around the negatively charged portion of the molecule. All right. Where would be some negative charged portions on this molecule, do you think, Fred?
On sugar there?
Yeah.
Well, okay, so when we see that sort of thing, what are we seeing?
Okay, that's a good question. So what we see here is, let me kind of sketch it first, right? We see, I'm drawing the left side of the molecule there. Here's our oxygen in between these two rings, right? Okay, so what we're seeing here, COH, OH, OH, right? So I haven't finished it completely, but I have enough for us to have a conversation. So what we're seeing here is each one of these is a carbon. Okay, now we've talked about this before, but just a little reminder. When we draw these compounds, these are organic compounds, right? And it saves a lot of time if we can just draw. So here's my organic way of drawing ethanol, all right? It's a lot easier than drawing a carbon bound to a carbon. This carbon has 3 hydrogens on it. This carbon has 2 hydrogens on it. This is an oxygen with another hydrogen on it. Okay, so this is my simplified way. You can see that there's the carbon, there's another carbon, and again, if there's not 4 bonds going to carbon, because carbon always needs 4 bonds going to it, then we assume, and I'll kind of put these on here lightly, that there are hydrogens, 2 coming off this carbon and 3 coming off that carbon there. All right, so each one of these little bumps here is a carbon. So if we have a hydrogen or oxygen here bound to this carbon and then bound to the hydrogen, right? That oxygen is going to have a partial what kind of charge?
Oh, partial negative.
That's right. And the hydrogen will have?
The partial positive.
That's right. So you have here a polar bond, here a polar hydrogen capable bond of doing hydrogen bonding. Here, 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 and here, right? So multiple spots in which hydrogen bonding can occur, and that makes sugar very soluble in water. All right, good job. Now, enthalpy of solution. Enthalpy of solution. Now, I don't know if you remember what this enthalpy of solution means, but enthalpy, that's the change in H, change in heat energy, associated with, in this case, the dissolution or dissolving of a compound into solution. All right. Now, we've talked about enthalpy of reaction, where you react one chemical with another, and the result is a release in heat energy, right? We talked about that in terms of this.
There aren't too many armies. You got to be a pretty developed country before you're going to be able to pull off packaging food for prolonged periods of time.
So in this video here, they show about the MREs.
Hi, I'm Stevie Hansen with Meal Kit Supply Canada. I'm here to talk to you today about our flameless ration heater. This is a flameless ration heater. What the flameless ration heaters do is they heat up the main courses and side dishes from our MREs. What I've got is...
MRE stands for meal ready to eat.
This is actually a side dish from our MRE. It's cornbread with stuffing. Open up the cardboard box and pull out the retort packaged side dish. This retort packaging I'm going to put within the flameless ration heater. So I'm going to tear off the top. I'm going to slide the retort packaged meal within the flameless ration heater and slide it down. Then what I'm going to do is I'm going to take about an ounce of water. There's a little line there that shows you how much water to put in. Pour in about an ounce of water. Tiny bit more. And it should start to steam immediately. See? I don't know if you can see it or not, but there's a little bit of steam coming out of there. It's starting to heat up. So what I'm going to do is I'm going to fold this over, and then I'm going to stick the entire thing back into the cardboard box. Then I'm going to lean it up against a rock or something. So I'm going to wait like 5 to 10 minutes, and I should have a nice hot meal.
No fire or stove is needed because the chemical mixture in the heater is activated with a small amount of water. The hot-pack non-magnesium flameless heater is odorless when activated, which is an important advantage to the soldier. No smell means no effect on the meal and no detection.
So this simple reaction here releases heat energy, right? And that's when we talked about delta H of chemical reaction. Remember, we have a chemical reaction, and if there's a release in heat energy, then we say the delta H is a negative value. Well, there is a change in heat associated with simply mixing compounds together. Even if there's not a chemical reaction, there will be a change, or there may be a change in heat. And that's because the intermolecular forces that are either needing to be overcome, or the new intermolecular forces that are being formed might be more favorable than the individual intermolecular forces associated with the compounds that are being mixed. That's a big mouthful here, but essentially let's look at this example here if we can. I have water here. All the water molecules have intermolecular forces with themselves. I have a solid piece of potassium iodide. There are intermolecular forces, and better to call them interatomic because it's just, or interionic because it's just potassium iodide, right? Potassium ions and iodide ions. But there are intermolecular forces, right? Electrostatic forces there. Hydrogen bonding forces here, right?
Yeah, okay, I get that.
Now, to pull these water molecules away from each other, it will require energy, right? Because they're interacting with each other, touching each other, and their intermolecular forces have a stickiness associated with them. Same with those of potassium ions and iodide ions here. In fact, do you remember what we call the energy associated with this lattice?
Oh, lattice. So that's the lattice energy.
That's right. The lattice energy is the energy necessary to take a three-dimensional lattice and separate it into its individual components, right? So if we think about the overall energy of this system, initially we have these two compounds that we're going to mix together. Before that mixing can occur, we can kind of think about molecularly or atomically or ionically what has to happen is these ions have to separate from each other. These ions have to separate from each other. And when they mix with, and that requires energy, and so we increase our overall energy by overcoming these lattice energy. And when we put the ions into this water, well, the result is new intermolecular forces which are formed. This would be an ion dipole interaction, right? Dipole because water can undergo a dipole-dipole interaction. Now, we don't call it ion hydrogen bonding because the potassium ion or the iodide ion, they don't hydrogen bond, right? But when they mix together, there will be a favorable stickiness associated with that, and so some energy will be released. Now, in this case, the amount of energy that's released compared to the energy of the unmixed compounds was a little bit higher, and so the result is a delta H, which is, if you look at this, 13 minus, so this is the delta H right here. It's a positive 13. So this was 13 kilojoules per mole higher than our starting point. That positive 13 here was the positive 632 to let's see. Oh no, this is looking at the 632 here and the 619 here. So the positive 13 means that this reaction, when those two mix together, actually is endothermic. It absorbs heat energy, and you'll feel the solution become cool to the touch. Have you ever done that before? Have you ever mixed a solid with a liquid and then feel that it feels cool?
No, I haven't.
Okay. I don't know if you've ever mixed a solid with a liquid and then feel that it gets hot, but that happens as well. And in that case, the resulting energy that's given off by the formation of the new intermolecular forces would end up being down here. So the resulting change in heat overall is a negative value, product minus wherever the reactants start from. Have you ever had those packets where they're either hot packets or cold packets, and you kind of crunch them up and then you hold them in your hands to either warm up your hands, or you might crunch them up and they get cold and you put them on part of your body. Maybe that's something that's sore that wants to cool down.
Yeah, I did that. I used to be on the football team, and when my knees got sore, they'd give me these cool packs.
Yeah, that's right. That's good. And have you ever dealt with the hot packs?
Yeah, on my mission. We were in a really cold area, and one of the members gave us these little packets, and you would just crunch them up, and then you could, what could you, oh, they'd be warm. They'd be warm on your hands.
That's right. All right, so hot packs and cold packs are examples of compounds that are separated, and then when you mix them together, the resulting shifting in intermolecular forces either requires energy or releases energy. All right, so this same type of thing can happen when you're mixing two liquids together, right? You can think about these two liquids, the energy necessary to separate, overcome those intermolecular forces of both of the liquids as they are, and then the energy associated with combining them together, right? So sometimes, again, the combination will result in a increased amount of energy released upon the intermolecular forces that are formed between the compounds, and sometimes it will be less favorable, and so it'll be a colder solution. Okay, and so here's an energy diagram for a scenario where the amount of energy necessary to overcome the intermolecular forces on the red compound, the amount of energy necessary to overcome the intermolecular forces on the blue compound, and then when you combine them together, the amount of energy that's released is exactly the same as the energy required to separate those intermolecular forces. The mixing of the two solutions is not exothermic, it's not endothermic. The delta H is 0 for that reaction. Okay, we can have the same scenario for gases mixing into solvents, right? Expanding the organic solvent and then mixing them together, right? In this case, delta H is endothermic. If a process is endothermic here, Fred, will the resulting solution feel cold or hot?
Let's see, which one? Exothermic means heat is given off to the surroundings, right?
That's right.
So I think the one on the right would be your solution. Your resulting solution would be warm.
That's right. So this would be an example of the mixing of these two compounds would feel cold. Here's an example of mixing these two compounds would feel warm. Okay, very good. Good place to stop.